Right, hello everyone. Okay, going through key assessment 4 on enthalpy, entropy, and free energy. So 4 multiple choice questions to start with. The first one, basically, as soon as you read that statement, you should know actually that that is not correct, and then you can quickly glance through the other 3, because the first ionization energy of anything is never going to be greater than the second ionization energy, and hopefully we all know why. Okay, question 2. Which one of the equations below represents a reaction that is feasible at all temperatures? And the only conditions where that arises is if we have delta H is negative and delta S is positive. So obviously you're quickly glancing through looking for that combination. Question 3. Which of the following reactions is there a decrease in entropy? So obviously you're looking at difference in state changes, but you know, a lot of these, they look similar: aqueous to aqueous and liquid and so on. So look at the number of particles. Yeah, so the answer is C, because this is the only one where there is a decrease in the number of particles, so that's going to give us a decrease in entropy. And question 4, being asked to calculate the standard entropy value for steam. You're given the equation here, you know how to calculate entropy values, products minus reactants. Obviously, we have to incorporate X because we're not actually given the value for H2O here, so it's 3x. Yeah. So you're writing an algebraic expression effectively and solving it for X. Okay. Okay, so question 5. Define using an equation. That's very important. A number of you didn't include an equation, and a number of you included an equation that went from the solid to the gaseous ions. So obviously, that if we're defining lattice enthalpy, it's obviously you've got to be forming the lattice from the gaseous ions. That's just a definition. You need to learn it. You know, it's a couple of marks there that some of you lost because you didn't give the specific definition. This part of the question, construct a Born-Haber cycle. So you have to have the Born-Haber cycle. A couple of you just did a calculation, but it specifically says construct the cycle, so you can't get marks if you don't do that. Including state symbols, which you should always include on a Born-Haber cycle, and then calculate the lattice enthalpy of magnesium chloride. So we, oh dear, it's not quite come out at the bottom of the page there. Okay, so this is our Born-Haber cycle. Crucial thing is to recognise that there are 2 chlorine atoms being formed, yeah, and 2 chloride ions being formed. So a number of you didn't incorporate that in your answer, but you were given some credit for it because there was a recognition that you might not, so you got 1 mark instead of 2, I believe. Okay, so the answer here, you can't quite see it at the bottom of the page, I'm sorry about that, the scanner. Right, so the calculation, what I've done is I've taken my positive lattice enthalpy and moved it over and taken my negative value here for enthalpy of formation and moved that over and made it positive, which to my mind just makes for an easier calculation. But you must remember that you have to then multiply both sides by -1 to get your final answer. So the final answer is -2526, and you must include the unit, kilojoules per mole. If on the exam paper the unit is already written, that's fine, but if there is no unit, you must write it in. So if you didn't, you lost a mark for that, and some of you did forget to do the calculation times -1, so you ended up with +2526. But you do get a mark for that, but not the full marks. Okay, so okay, here, so when you're explaining, you're comparing lattice enthalpies of different substances, you are basically looking at the charge density on the ion and the size of the ion. So do this in a kind of structured way. Yeah, you've got to look at all of the ions, and it's very important that you use the correct terminology. Some of you are talking about molecules, some of you are talking about atoms. That's a definite, you just won't get marks if you put those kind of terms in. You're talking about ions and only ions. Okay. So just, you know, compare the two metals. You've got charge difference and you've got a radius difference. So you need to discuss charge density. And then if we're looking at the negative ions, again, they've got the same charge, so you can make that comment, but chloride is smaller than bromide. So the strongest attraction is going to be between the magnesium chloride, because magnesium has a greater charge density and it's smaller, and chloride is smaller than bromide. So effectively they can get closer together, so the ionic bond will be stronger. Okay, right, so again here, right, you had to complete this Born-Haber cycle, right, given information in this table, right, okay. Now the crucial thing here that some of you didn't do is you didn't actually look to see what was the enthalpy change that was taking place. So here we've got sodium solid, forming a gas, so that's atomization of sodium. But then, kind of out of the normal sequence that you would maybe do, you're going sodium gas to sodium ion. So some of you put the wrong value in here, and that's, you know, quite a common trick, I suppose, used in an exam question where they're actually testing you to see if you really understand what this Born-Haber cycle is showing you. So we're going from the solid to atoms to ions, and then we're forming atoms of oxygen from O2 to O. Yeah, don't forget to put the electron in, of course, once you've got ionization. I think most of you got this bit right because it's a bit more obvious, your electron affinity, the first electron affinity, second electron affinity. Okay, so just be careful to check when you're asked to fill in a Born-Haber cycle that the Born-Haber cycle is in the sequence that you would expect, and if not, double check your values. And then obviously it's a straightforward calculation, same as the other one. I just find it easier to move my positive lattice enthalpy over here and move this over and make it positive, do the sum, and then multiply both sides by -1. But obviously if you don't want to do that, you feel that confuses you, you forget about the -1 thing at the end, okay, well just move all of these over to this side. But don't forget, you've got to change the sign of all of them. Okay. And then part C, which one of the following compounds has the most exothermic lattice enthalpy? So effectively they're saying which one has got the strongest ionic bonds. Yeah. So straight away you should recognise that it can't be either of the potassium compounds, because potassium's got a bigger radius than calcium. Yeah? And then it comes down to the bromide and the chloride. Okay, so again, explain your answer in terms of the ions present, and some of you didn't do that, and again you use the wrong terminology, so you can't get marks. You start talking about molecules and atoms. So you just be methodical in the same way as you were with the last one. Look at your chloride and your bromide. Same charge, but higher charge density on the chloride. You know, this is the terminology you should be using. Charge density. Ca2 plus potassium. Difference in charge, but also difference in size. Okay. Okay, so two questions here on enthalpy change of solution, but both very similar. So, you know, if you got one right, you should really have got the second one right. I don't know why, but you seem to be reluctant, a lot of you, to draw, just scribble out a quick Born-Haber cycle, which to my mind is the easiest way to see this. Make sure that you look to check whether this is lattice enthalpy of formation or dissociation, but because it's negative, we know it's formation. And actually say, but just be careful to check that in any question on solution. Yeah, so you're forming your lattice, you're hydrating the ions, so you've got your ions at the top, you've got your ionic lattice at the bottom. You're going to hydrate the ions, so there's some kind of energy change here, and then obviously the dissolving the ionic lattice is enthalpy change of solution. But once you've drawn this, you're just following the arrows round, yeah? So minus 960 plus X, yeah, is equal to the hydration enthalpies of the ions, and then do the calculation. Exactly the same here. The only difference obviously is that we've got 2 fluoride ions here, so you need to multiply the value by 2. Okay, so question 9. Question 9 suggests how the quantities of delta H, delta S and T can be used to predict whether a change is feasible. I mean, all you're doing really is giving the equation and saying that as long as G is less than 0, or 0 or less than 0, then the reaction will be feasible. Okay. Okay, part B here, explain why the evaporation of water is spontaneous even though it is endothermic, that process. Okay, so we're looking at the change in state, so we're going from a liquid to a gas, which will mean that our delta S is positive. This endothermic, we know that delta H is also positive, so it's not going to be a straightforward, oh yeah, so it's always going to work. You need to look at the feasibility of it, and it's definitely going to depend on T delta S here. Yeah. So once the temperature is high enough, that term will be bigger than delta H, and the process will become feasible. Yeah. So for water to evaporate, the temperature must be high enough to make delta G less than 0, 0 or less than 0. Okay. All right, so you're asked to calculate, you're given some data on entropy and enthalpy, and you're asked to calculate the temperature above which the reaction between hydrogen and oxygen to form gaseous water is not feasible. Yeah, so we want to know when it's not feasible. So write your equation for the formation of gaseous water from your hydrogen and oxygen. And obviously here, because we're being asked about temperature, we're going to make our delta G 0 and rearrange our equation. So temperature will be equal to delta H over delta S. You need to calculate your delta S value from the table. So we've got water here as a gas, 189. Oxygen 205, and hydrogen is 131. So yeah, so we've got 189 for our delta S because that's our product for water. Half of oxygen because it's half O2 plus 131, which is the entropy for hydrogen, and the answer to that calculation is minus 44.5 joules, remember, per Kelvin per mole. So that's your delta S value. So don't forget you're going to need to convert that, yeah, when we're looking for the temperature, because our delta H is in kilojoules per mole. So we just take that directly from the table, minus 242. Divide it by the value you've just calculated, but remembering to convert it to kilojoules, and the temperature comes out at 5,438 K. Okay, you have to put the unit in. A number of you lost a mark because you didn't write a unit. I just don't understand how you can look at a number and not see that you have to put a unit there, otherwise it doesn't mean anything. The number 5438, yeah, on its own doesn't tell you anything, so you must put that unit in. Okay. And then the last part of this part C of this question, state what would happen to a sample of gaseous water that was heated to a temperature higher than 5,438 K, and give a reason. Okay, now obviously what's going to happen, if the temperature is higher than this, the temperature will be feasible in the opposite direction. Yeah. So what will happen is it will turn back into your hydrogen and your oxygen effectively. So decompose to hydrogen and oxygen. And the reason for this is that the delta G in that direction will be less than 0. And if you don't understand what I'm saying and you're thinking, well, it doesn't make sense, actually do the calculation in reverse. Yeah, use the equation so that you've got your these will be your products and this will be your reactant. Work out your delta S, which should come out to positive 44.5. Put that into your equation and you'll see that delta G comes out at less than 0. So above that temperature, that's what would happen. Okay. Okay, so the last part of the question, when hydrogen is used as a fuel, more heat energy is obtained if the gaseous water is condensed to liquid water. And then it says use the entropy data from the table to calculate the entropy change when 1 mole of gaseous water is condensed at a given temperature. Assume that the free energy change for this condensation is 0. So obviously we're going to go back to our table and we're going to need to use these two values. We've got our entropy value for gaseous water and our entropy value for liquid water. Okay, so to calculate the entropy change here, we need to subtract the entropy for the gaseous form of water from the entropy of the liquid form of water, which gives us a value of -119 joules per Kelvin per mole. If delta G is 0, then we know that delta H is equal to T delta S. Yeah, so it's just a rearrangement. So we're looking for, normally with this rearrangement, we're looking for temperature, but actually this time we're looking for delta H. We've been asked to calculate entropy change. So we're given a temperature, 373, times -119, and that's our entropy value, change in entropy. But don't forget, enthalpy is in kilojoules per mole, so we're going to need to divide the answer by 1,000 to give us kilojoules per mole. Do the calculation, and hey presto, here we are. Don't forget to put your units in again. There are no units written on this question, for you to write your answer in. So you must put your units in yourself. Okay, good. Well done, everyone. Hopefully that's helped. And make sure you complete the follow-up questions. And then if you've got any other issues, you need to come and see me, preferably in the early session on Thursday morning. Thank you. Goodbye.